Hello students, today we are going to continue with chapter 1 of the AP Chemistry Material, Atomic Structure and Properties. This is part 2. The first topic we are going to study today is the empirical and molecular formulas. They are an easy topic, so don't be afraid of the name. However, you will also need to know how to determine the empirical and molecular formulas of a compound, given masses or mass percent of the component of that compound. Remember that the empirical formula represents the simplest ratio of one element to another in a compound, which is CH2O, for example, while the molecular formula represents the actual formula for a substance. Now, I need you to understand how to differentiate between empirical and molecular. Okay? Now, it is actually simple. Empirical formula, you can't divide the number of the atoms in it. So, for example, if I give you that CHO, CH2O, the numbers of the atoms of the carbon and the oxygen is actually 1. That's why we didn't write it, and we normally don't write it. This time I wrote it just for explanation, okay? So, the question here is, can you divide all the atoms in one single number? Actually, you can't, because the carbon is 1, and the hydrogen is 2, and the oxygen is 1. There is no number that you can divide all the numbers using it, and it will produce a whole numbers. Okay? So for another example, we have C6H12O6. So this is a molecular formula. Why? Because you can divide the numbers of the compound. Okay, so we have 6, 12, 6. We can divide all of them using the number 6. And the product will be C1 H12O1. Sorry, H2O1. Okay, H2O1. So basically, whenever you can divide the number of the atoms, it is molecular. Whenever you can't, it is empirical. However, sometimes we might have an empirical formula which is at the same time it is an molecular formula. So for example, if we take this type of aldehydes, which is CH2O, this is at the same time empirical and molecular. Why? Because it is empirical because you can't divide the numbers, and it is molecular because it actually represents the real molecule, which is some kind of aldehyde. Okay? So, this is empirical and molecular at the same time. I need you to understand that sometimes we will have a formula that can be both empirical and molecular at the same time. Now we have a question that we are going to solve together. A compound is found to contain 56.5% of carbon, 7.11% of hydrogen, and 36.4% of phosphorus. Determine the empirical formula for the compound. So we are going to use a basic method in order to solve this question. Okay? I want you to write the name of each atom included in this equation. So first of all, we have carbon, okay? So this is carbon. And we have hydrogen. So this is the hydrogen. And we have phosphorus. So this is the phosphorus, okay? Okay. Then we are going to write moles for each one of these. So we are going to find the moles of the carbon. We are going to find the moles of the hydrogen and the moles of the phosphorus. Okay? So, moles, as we have studied previously, it equals to mass over molar mass. The mass here is given as a percent. You are going to put it as mass. So, we are going to write 56.5 a gram, not percent, because actually this percent represents the gram. Okay? So, we have 100%. This 100% will represent the number of 100 gram. Okay? Okay. So when I give you 50%, in this type of questions, which is the empirical formula, when I give you this type of a question, this percent will represent the mass number, okay? The mass of the element. So basically we have the mass of the carbon, we have the mass of the hydrogen, which is 7.11, and we have the mass of the gram, of course, and we have the mass of the phosphorus, which is 36.4 gram. Now we need to find the molar mass using the periodic table. Using the periodic table, you will find that the molar mass of the carbon is 12.01, the molar mass of hydrogen is 1.008, and the molar mass of phosphorus is actually equal to 30.974. Okay? Okay. Now we are going to find the moles of each of these elements. We are going to find the moles of each of these elements using the calculator. 56.5 divided by 12.01, it will equal to 4.7. Okay, so equal to 4.7. And for the hydrogen, 7.11 divided by 1.008, it will equal to 7.05. And for the phosphorus, 36.4 divided by 30.974, it will equal to 1.18. Okay, so now we have found the moles of each element. Okay, so we are going to write mole, mole, and mole. This is for carbon, this is for hydrogen, and this is for phosphorus. The last step, in order to find the empirical formula, is to divide using the smallest mole number. So the smallest mole number here is the phosphorus number. So we are going to divide all these elements using the mole number of the phosphorus, which is the smallest, which is 1.18, 1.18, and 1.18. Okay, so carbon will be, hydrogen will be, and phosphorus will be. Now using the calculator again, 4.7 divided by 1.118 equal to almost 4, because it is a 3.98 and we need a whole number. We don't need fractions. The hydrogens is 7.05 divided by 1.18, it's equal to 6. And the phosphorus is 1.18 divided by 1.18, which is equal to 1. So basically we now found the empirical formula, which is CHP. Okay, the C is 4, the H is 6, and the P is 1. Okay, so this is 1. We don't write the number 1 for the elements. This is called empirical formula. This is called empirical formula. Why? Because you cannot divide all these elements number with one single number. Now another question for the molecular formula now. If the compound has a molar mass of 170.14 gram per mole, what is its molecular formula? Okay, now in order to find the molecular formula, we need to find the molar mass of the empirical formula. Now look here, look here. We are going to find the X number. What X represents is the number that we are going to multiply by the empirical formula in order to find the molecular formula. So it is equal to molecular mass, which is given in the exam, okay, and in the question, divided by the empirical mass. Okay, so it is equal to, the molecular mass is given 170.14 gram per mole, divided by the empirical formula mass. As you can see here, we have 3 different elements, so we are going to open 3 different parentheses between each one and the other plus sign, okay? And inside of it, we are going to put a multiplication sign. So first of all, we have carbon, which has 4 atoms, so 4 times its molar mass, which is 12.01. And then we have hydrogen, 6 hydrogens times its molar mass, which is 1.008. And finally, the phosphorus, which is 1 phosphorus times 30.947. Okay? 30.974, sorry, 0.974. Now, I'm going to use the calculator in order to find the final answer. The final answer is 2, okay? So x equal 2. Again, what x represents, it is the number that we are going to multiply it by the empirical formula. So the empirical formula is C4H6. You don't need to put these spaces between the elements. I'm just putting them in order to explain to you how to solve the question, but don't do it in the exam. Okay, so it is times 2, because we have 2 here, times 2, and this is 1 times 2. So the final answer, which is the molecular formula, will be C8, 4 times 2, H12, 6 times 2, and P2. So this is the molecular formula. Electron configurations and the periodic table. Again, this topic, we are going to study it expandedly later. The positively charged nucleus, and the nucleus actually is positively charged. Why is that? If we assume that this is a nucleus, the nucleus actually contains 2 different parts. The first one called protons, and the second one called neutrons. The protons are positively charged, while the neutrons has no charge, which is a neutral, okay? They are neutral in charge, okay? So the whole nucleus is positively charged because of the protons, while the orbits around the nucleus, which contains the electrons, are actually negatively charged because the electrons are negatively charged. So the positively charged nucleus is always pulling at the negatively charged electrons around it. And the electrons have potential energy that increases with their distance from the nucleus. So the potential energy usually increases when the electron is becoming farther from the nucleus. It works the same way that the gravitational potential energy of a brick on the 3rd floor of a building is greater than the gravitational potential energy of a brick nearer to ground level. So, the energy of electrons, however, is quantized. What do I mean by quantized? It is very important definition here, is that it can it has exactly specific energy levels. Very specific energy levels. That's important. It means that electrons can exist only at a specific electrons level, okay, or a specific energy level. So let's say that, okay, let's say that this is a nucleus, okay, this is the nucleus that contains the protons and the neutrons, and around the nucleus we have orbits, okay. Now the electrons can only be found in the orbits, okay, and you will never find any electrons between the orbits. You can't find any electron between the orbits. So the electrons are quantized because they only can be found in the orbit itself, okay? So specific energy levels separated by specific intervals. It is similar to a situation in which the brick in the building could be placed only on the 1st, 2nd, or 3rd floor of the building, but not in between. Okay. Coulomb's law. The attraction between opposite charges is known as an electrostatic force, and it depends on the charges and distance involved. This can be calculated using Coulomb's law. Now, as we mentioned before, the nucleus is positively charged, and around the nucleus there is orbits that contain electrons with a negative charge. So basically we have opposite charges, as we mentioned here. There will be an attraction between these opposite charges. This attraction is electrostatic force, okay? And it depends on two different things. The first thing is the charges, and the second thing is the distance involved between them, okay? So this can be calculated using Coulomb's law. F Coulombic equal Q1, which is the first charge, Q2, the second charge, R squared, which is the distance between them. So F is electrostatic force between the nucleus and an electron. Q1 is the magnitude of the positive charge, nucleus. You can put Q1 as the negative charge. It's okay. It doesn't matter. Q2 is the magnitude of the negative charge, which is the electron. And the R is the distance between the charges. While on the exam, you will not be required to mathematically calculate the force between these particles, which is good news. You should be able to qualitatively apply Coulomb's law. Essentially, the greater the charge of the nucleus, the greater the force is between it and an electron. So you need to understand the concept that F equal Q1, Q2 over R squared. So basically, whenever the Q is larger, which is the charge, whenever the charge is larger, the force will be larger. Whenever the distance is larger, the force will be smaller. Did you get it? Okay. As a result, electrons feeling the influence of more positively charged feel a stronger pull from the nucleus and have lower potential energy. Regardless of the charge magnitudes, if two opposite charges are closer together, meaning the value of R is lower, the force between them is higher. So again, we have a charge value and we have distance value, okay? And we have the force value. If the charge was greater, the force will be greater. If the distance was less, the force will be greater. Now, if the charge was less or smaller, the force will be smaller. And if the distance was higher, the force as well will be smaller. Okay. Electrons closer to the nucleus feel a stronger pull. Why? Because the R is smaller. Okay. And thus have lower potential energy than electrons further away because of the distance and because of the energy they will be forced to. In order to remove an electron from an atom, this electrostatic attraction must be overcome by adding energy. The energy needed is called the binding energy. This is a very important topic that we are going to study later, of the electron, and is always a positive value. So the binding energy of an electron is always a positive value because we always need to give the atom energy in order to release that to release that electron. Another way, to remove the electron from the atom. The Bohr model, he is one of the greatest scientists in the history, and he made a model. Now, Niels Bohr took the quantum theory and used it to predict that electrons orbit the nucleus at a specific fixed radii, as we mentioned before, like planets orbiting the sun. So for example, this is the nucleus. Around the nucleus we have orbit 1, orbit 2, orbit 3, 4, 5, 6. Now in these orbits, the electrons will be inside of them, not between them, okay? So in order to move one electron from one orbit to a higher one, the atom needs to absorb energy. And in order to release one atom from higher level to lower level, the atom will emit energy. Again, in order to move an electron from n equal 2 to n equal 4, what is going to happen? The atom will absorb energy. If we are going to move the electron from n equal 6 to n equal 1, so we are going backward, okay? The atom will emit energy, okay? Each energy level is represented by a row on the periodic table. there are currently 7 known energy levels, which correspond with n equal 1, which is period number 1, to n equal 7, which is period number 7 in the periodic table. The closer an energy level is to an atomic nucleus, the less energy electrons on that level have. Okay, so let's explain this further. Okay, so for example, this is the nucleus. Okay, around the nucleus we have 1, 2 orbits, 3 orbits, 4 orbits or energy levels, 5 energy levels. Okay, now if I ask you which one has higher energy, is it the electron in the second energy level or the electron in the fifth energy level? Your answer should be that the one farther from the nucleus is the one with the higher energy. So basically the one in the fifth energy level is higher in energy than the one in the second energy level. Okay? Okay. Now, while the Bohr model is not a perfect model of the atom, it serves an excellent basis to understand atomic structure. When atoms absorb energy in the form of electromagnetic radiation, electrons jump to a higher energy levels, which we called it previously that energy absorbed by an atom. So if the atom was in level 1 and then absorbs energy enough to transfer it to level 2, it will go to level 2. If it absorbs more energy, it will go to level 3, 4, etc. And when electrons drop from higher to lower energy levels, this is called emission. When the electron is in a group or in energy level 5 and it emits energy, it will go back to energy 3, 4, 5, energy 3, 4, 2 or 1 level. Okay? Atoms give off energy in the form of electromagnetic radiation. You need to memorize this name, which is electromagnetic radiation. It is the form of energy that will be released from an electron when it emits energy. Photoelectron spectroscopy. It is one of the most important topics in this chapter. Again, it is called photoelectron spectroscopy. If an atom is exposed to electromagnetic radiation at an energy level that exceeds the various binding energies of the electrons of the atom, the electron can be ejected out of the atom. The amount of energy necessary to do that is called the ionization energy. Again, what do we mean by ionization energy? It is the amount of energy needed to eject an electron from an atom. For that electron. For the purpose of this exam, ionization energy and binding energy can be considered to be synonyms terms. Okay, so again, ionization energy and binding energy are synonyms in this exam. When examining the spectrum for electrons from a single atom or a small number of atoms, this energy is usually measured in electron volts, which is EV. EV abbreviated for electron volts. 1 electron volt equal 1.60 times 10 to the power of negative 19 to the power of negative 19 joules. Okay? If moles of atoms are studied, the unit of the binding energy is usually either kilojoule per mole or mjoule per mole. The m here represent megajoule, so it is a megajoule per mole, which is 10 to the power of 6. All energy of the incoming radiation must be conserved, and any of that energy that does not go into breaking the electron if free from the nucleus will be converted into kinetic energy. The energy of motion. What do we mean by kinetic energy? It is the energy of motion for the ejected electron. So, for example, if an electron needs 1 kilojoule in order to leave the atom or to be ejected out of the atom, and you gave it 2 kilojoules, the first kilojoule will be used in order to eject the atom out of the to eject the electron out of the atom, and the second kilojoule will be used as kinetic energy. So incoming radiation energy will be binding energy plus kinetic energy of the ejected electrons. The faster an ejected electron is going, the more kinetic energy it has. So the faster the electron, again, the more kinetic energy it has. So if you want the electron to be faster, you are going to increase the amount of kinetic energy it has. Electrons that were originally further away from the nucleus requires less energy to eject and thus will be moving faster. So let's explain this further. Okay, so for example, we have the nucleus. Around the nucleus we have only two orbits. We are going to use them to explain this line. Okay, then we have one electron in the first orbit and another electron in the second orbit. In order to eject this electron out of the atom, we need to give it energy to leave the whole atom. So we need an energy to move it from level 1 to level 2, then to move it from level 2 outside the atom. While for the electron in the second level, we need to give it energy just to leave from the second level outside the atom. So the higher in energy level the electron is, the less energy needed to eject the electron and the faster the electron will be after ejection. Okay? So by examining the speed of the ejected electrons, we can determine how far they were from the nucleus of the atom in the first place. So if we have 10 electrons that were ejected out of the atoms, or out of one atom, and we applied the same energy for the whole electrons, we can determine by the speed of the electrons how far they were from the nucleus. So if it was very fast, this means it is in the second orbit. If it was slower, this means it is in the first orbit. Okay? Usually it takes electromagnetic radiation in either the visible or ultraviolet range to cause electron emission. Again, how to emit an electron? We need electromagnetic to be in the visible range or in the ultraviolet range. Okay? Okay. While radiation in the infrared range is often used to study chemical bonds. Okay, again, what do we need? The infrared range of electromagnetic radiation. It will be used to study the chemical bonds. Okay, to study the chemical bonds. Radiation in the microwave region is used to study the shape of the molecule. Again, the radiation in the microwave region will be used to study the shape of molecules. Again, we have visible and ultraviolet region will be used to emit electrons. We have the infrared region will be used to study the chemical bonds, and the microwave region will be used to study the shape of the molecules. Now we need to understand the spectra out of the spectroscopy. If the amount of ionization energy for all electrons ejected from a nucleus is charted, you get that is called a photoelectron spectrum, which is PES, photoelectron spectrum. That looks like the following. Okay, so we have the binding energy, we have the relative number of electrons drawn in this scheme. The y-axis describes the relative number of electrons that are ejected from a given energy level, and the x-axis shows the binding energy of those electrons. Unlike most graphs, binding energy, ionization energy, decreases going from left to right in the PES. So the binding energy will decrease going to the right of the x-axis. The spectrum above is for sulfur. This is for the sulfur. This spectrum is for the element sulfur. Each section of peaks in the PES represent a different energy level. Because there are multiple peaks in each section, we can tell that not all electrons in the same energy level are located at the same distance from the nucleus. Okay? With each energy level, there are subshells which describe the shape of the space of the electron can be found in. Remember, we are in a three-dimensional space here. The Bohr model is limited to 2 dimensions and does not represent the true position of electrons. Due to that reason, electrons do not orbit the nucleus as planets orbits the sun. Instead, they are found moving about in a certain area of space, the subshell, a given distance, the energy level away from the nucleus. So we have subshells in each energy level. So for example, if we are talking about energy level number 1, it actually contains only one subshell, which is S. If we are talking about energy level number 2, it has only 2 subshells, which is S and P. If we are talking about energy level number 3, we have 3 subshells, which is S, P, and D. Okay? In all energy levels, the first subshell is called the S subshell and can hold a maximum of 2 electrons. So basically we have S subshell, P subshell, D subshell, and F subshell. S subshell can only hold 2 electrons maximum. P can hold the maximum of 6 electrons, D 10 electrons, and F 14 electron. Okay? Okay. Now, the second subshell is called the P subshell and can hold a maximum of 6 electrons. In the spectrum on the previous page, we can see the peak for the P subshell in energy level 2. This is the peak of P subshell. Because it holds 6 electrons, it is higher than the other peaks. Okay? So this peak here represents 2 electrons. This peak here represents another 2 electrons. So we are going to learn how to do electron configuration, but now just for explanation, we have 1s2, 2s2, and 2p6. As you can see, these are equalized in height and they hold 2 electrons, and this one as well is equalized in height, so it is 3s2 and hold the same amount of electrons. This long one or height one has 6 electrons, and this one here probably has 3 electrons, which is 3p3. As we mentioned, P can hold the maximum of 6 electrons, but as well it can hold 1, 2, 3, 4, 5 electrons as well. Okay? Okay. Now energy level 2 is 3 times higher than that of the S subshell. The relative height of the peaks helps determine the number of electrons in that subshell. Okay. In the area for the third energy level, the P subshell peaks is only twice as tall as the S subshell. This indicates there are only 4 electrons in the P subshell of the particular atom. Now, here we assume that it is 2 electrons, but it is actually 4 electrons. And how we found that it is 4 electrons? Now, you are going to use a ruler for this purpose, okay? You are going to measure the height of this peak, which we know that it holds 2 electrons, and you are going to measure the length of this peak, and you are going to take the ratio between them. So for example, this is a 2 centimeter and this is a 4 centimeter. So you are going to say 4 divided by 2 equal 2. So it is twice the number of the atoms in the known one. So the known one has 2 electrons. Therefore, the unknown one will hold 4 electrons. Now we are going to start studying the electron configuration in order to solve the questions of the PES more properly. Studying the PES of elements allows scientists to understand more about the structure of the atom. In addition to the sand P subshells, 2 other exist. D hold 10 electrons and F hold 14 electrons max. The periodic table is designed so that each area is exactly the length of one particular subshell. So as we mentioned before, the first 2 groups, which is group 1 and group 2, and we can call it group 1A and group 2A, they called S block, and block D actually contains the groups from 3B to 12B, or we can call it 3 to 12 without the letter B. And the P block is actually contain the groups from 13 to 18, or we can call it from 3A to 8a. Okay, while these below are the actinides and actinides, the lanthanide and actinides, and they are called the F block. As we mentioned previously, S block can actually hold 2 electrons, therefore it has 2 groups, and D block can hold 10 electrons, therefore it has 10 groups from 3b to 12b. P block can hold 6 electrons, therefore there are 6 groups from 13 or 3a to 18 or 8a. And for the F block, it is 14 group, okay, because it is called F block. It holds 14 electrons. There is a very important note here that this element here, which is the helium actually have s electrons. It ends with 2s or 1s2 electrons. So it should be positioned right here in the second group, as long as it ends with the s electrons. But we put it here because it is a noble gas. So we put it with the other noble gases in group 8a or 18. As you can see, the first 2 groups plus helium are in what is called the S block. The groups on the right of the table are in the P block, while transition metals make up the D block and the F block. And the inner transition metals below the table inhabit the F block. The complete description of the energy level and subshell that each electron on an element inhibits is called its electron configuration. Now we are going to study how to make an electron configuration for one element, and I want you to understand one thing here, okay? Okay. So basically here we have 7 periods, period 1, period 2, period 3, period 4, period 5, 6, and 7. So I'm going to write 1, 2, 3, 4, 5, 6, and 7. As you can see here, this is the S block. So we are going to give S for each of these letters, okay? So S, 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 S. Then, in the blue color, we are going to start with the P block because it aligns after the S, okay? So the P block has 6 groups, right? And it starts from period number 2. Because the first element here, helium, as we mentioned before, it should have been put here in the second group, but because it is a noble gas, it was put in the last one. However, so the P block will start from the second period, so we are going to start writing from 2 until we reach the number 7. So 2, 3, 4, 5, and 6, and 7. And we are going to mention that these are P block. So P, P, another P, 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 P. Okay. Then we are going to start with the D block. This is the D block here. This is the D block here. Okay. As well, it will start from the period 4, but however, it is actually going to start from period number 3. But for other purposes, it was put in the 4th period. When you do the electron configuration, you will start from the number 3 till the number 6, okay? So it is 3, 4, 5, 6, and you are going to put D for each of these. So, again, the first S is in the period 1, the first P is in period number 2, the first D is in period number 3, and of course the first F is in period number 4. So the first F is in period 4, and the second F is in period number 5. Okay? Now, we are going to learn how to read these numbers. Okay? So, basically, we are going to make diagonal lines. The first diagonal line will only contain the first letter, which is 1S. The second one as well will hold one element, which is 2S. The third line and the fourth line together will hold 2 elements each. The fifth and sixth element or line will hold 3 different elements. Okay? You need to learn how to do this. And the 7th line will hold 4 elements, and the last one will hold another 3. So how we are going to read this electron configuration scheme, and actually it is very important because we are going to use it a lot in order to solve many types of questions. So please, you need to memorize how we have done it, okay? So we are going to read each line uphill to downhill, okay? So the first line starts with 1s, so we are going to write 1s. Then the lines will end. The second line will start with 2s, and then the line will be ended. The third line will start with 2p, then 3s, so we are going to write 2p, then 3s. The fourth line will start with a 3p, then 4s, this is a 3p, and then we have 4s. The fifth one will start with a 3d, 4p, and finally 5s. Then you are going to start with the next line, etc. Okay? Okay, now, we need in this question to solve for sulfur. This is sulfur, okay? This is sulfur. It has 16 electrons. So basically, we are going to solve for 16 electrons, and we need to use all of these 16 electrons, okay? So we are going to start with 1s. S can hold 2 electron maximum, okay? So we use the 2 electrons. We have 16 electrons to use. We took 2 of them, so we have 14 electrons left with us to use. Then we have 2s. The 2s as well can hold 2 electrons, so minus 2. We have 12 electrons to go. Then we have 2p. P can hold 6 electrons, as we mentioned before. So minus 6, it equals to 6. So we have 6 electrons to go. Then we have a 3s, which can hold 2 electrons. So minus 2 equal 4 electrons. Finally, we have a 3p. A 3p can hold 6 electrons, but we don't have 6. We have only 4 electrons. So we are going to put the 4 electrons that we have minus 4 equals 0. And now we have used the whole electrons. Now, this is the first method in order to solve for electron configuration. Okay, this is the first method. Now, there is a second method that we need to learn. Okay, just let me erase what we solved here. As well, we are going to use the scheme that we just learned how to do it. Okay, so we have S16. So I'm going to write S. It has 16 electrons. Now, the method is easy. You need to determine in which period your element is. This is my element. I'm going to the left. It is in the third period. So you will start solving by writing a 3s, because we always start with the subshell S. We always start with the subshell S. Either it was 4th period, 5th, 6th, etc. You will write 1s, 2s, 3s, 4s, etc. Okay? Okay. Then you need to determine the noble gas in the previous period. Again, we are in period number 3. We are going to the previous period, which is period number 2. We are going to the noble gas of this period, which is the last element, which is Ne. Okay, so we are going to put the Ne between the brackets. The Ne actually holds 10 electrons. We are going to write 10 electrons here. And we are going to start by subtracting the 10 electrons that were used for the noble gas. So 16 minus 10 equals 6. So basically we have 6 electrons to solve them. Okay, so the 3s will hold 2 electrons minus 2 equal 4. And after the 3s, this is the 3s in the third line. It is finished, so we are going to start with the fourth line. The first element in the fourth line is a 3p. Okay, so I am going to write a 3p. The p can hold 6 electrons, but actually we have only 4 electrons left, so we are going to write 4 electrons. Minus 4 equal 0. And again, we solve the question with different method. This method actually uses the noble gas notation. It uses the noble gas notation. In the exam, you can be asked to solve using either ways, okay? Therefore, you need to learn both of them, okay? Another question here, we need to solve for nickel. We need to solve for nickel, okay? We are going to solve using both of the methods that we have studied previously. The first method, we have 28 electrons in the nickel. We are going to start with the first line that holds 1s, so we are going to write 1s. It will hold 2 electrons minus 2 equal 26. Then we have 2s, okay, this is 2s, holds 2 electrons minus 2 equal 24. Then we have the third line, it starts with 2p, so 2p can hold 6 electrons minus 6 equal 18. Then we have the 3s that will hold 2 electrons minus 2 equals 16. Then we have the fourth line, it starts with 3p, so we are going to write 3p. It will hold 6 electrons minus 6 equal 10. Then we have 4s, 4s can hold 2 electrons, so minus 2 equal 8. Then we have 3d, 3d can hold 10 electrons, and we have 8 electrons left, so we are going to put the 8 electrons. Okay, so we have solved minus 8 equals 0. So we have solved this question using the first method. Now I'm going to erase the solution and resolve it using the second method, which is using the noble gas notation. Okay? Okay, so first of all, I'm going to write the Ni, which is the nickel. It has 28 electron. Okay, now I need to determine in which period it is. It is in period number 4. So we are going to write 4s. Then we are going to put brackets here in order to put the noble gas in the previous period. So we are going to the previous period, which is period number 3. We are going to the last element, which is Ar, which is the noble gas. It is Ar 18. It holds 18 electrons. So we are going to subtract the number of electrons we have, the 18 electrons from the number of electrons we have. So minus 18, which is equal to 10. Then we have 4s. The 4s will hold 2 electrons. Okay, so minus 2, it equals to 8. Then we started from 4s. This line is finished. We are going to start with the next line, which starts with 3d. So I'm going to put 3d here. The 3d can hold 10 electrons. However, we have only 8 electrons left, so we are going to write 8 minus 8 equals 0. Again, we solved the question. Now there is a very important note here. I want to give you that D cannot hold 4 electrons or 9 electrons. It will take 1 electron from the S before it, and the D4 will become D5, and the D9 will become D10. Okay, so let's take an example regarding this topic. Okay, so just let me erase the solution here, and we are going to solve for Cr, which is chromium. Okay, this is Cr, chromium. It has 24 electrons. We are going to solve using the second method, which is the method of determining the period number, then determining the noble gas in the previous period. So this is the period, which is 4, so we are going to write 4s. Then in the bracket, we are going to put the noble gas in the previous period, which is period number 3. The noble gas is Ar18, so this is Ar18 minus 18. We have 6 electrons left. The S here will take 2 electrons minus 2 equal 4. Then after the 4s, again, this line is finished, and we are going to start with the second line, or the next line, which has 3d as a start. The 3d will take 10 electrons. However, we have only 4, so we are going to put the 4 electrons here. Minus 4 equals 0. Now, regarding the note, we just mentioned D cannot hold 4 electrons or 9 electrons. It will take 1 electron from the previous, from the previous S. So this S had 2 electrons, now it is only 1. And this D had 4 electrons, now it is 5. This is the electron configuration of the elements that ends with D4 or D9. It will always take 1 electron from the previous S subshell. The Aufbau principle, one of the most important principles that you need to understand. The Aufbau principle states that when building up the electron configuration of an atom, electrons are placed in orbitals, subshells, and shells in order of increasing energy. So basically, the scheme that we studied previously and we learned how to draw. Just give me a second, okay? This scheme that started with 1, 2, 3, 4, 5, 6, 7, 8, or without 8, sorry. Then S, 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 then 2p, 3p, 4p, 5p, 6p, then 3d, 4d, 5d, 6d, and here we have 7p, then 4f, 5f, and we have done the diagonal lines, and we've learned how to read these lines, okay? Now these actually arranged based on the energy of each subshell. So if I asked you which one has more energy, okay, which one has more energy? Is it 4p or 3s? The answer will be 4p because you are going to go to the lines, the first line, the second line, the third line, okay, our element is here, is 3s. Then fourth line, fifth line, our second element is here, which is 4p. So as long as the 4p came after the 3s, it has more energy. So if it came after the element, it has more energy than it. So the lowest energy here is 1s, then 2s has a little more, 2p a little more, 3s a little more, 3p, 4s, 3d, 4p, 5s, etc. Okay? Now the other principle here is called Pauli exclusion principle. The Pauli exclusion principle states that the two electrons which share an orbital cannot have the same spin. One electron must spin clockwise and the other must spin counterclockwise. Now, we have studied that we have subshells called S and P and D and F. Each one of these subshells holds electrons, okay? And we said that the electrons S can hold 2, P can hold 6, D can hold 10, and F can hold 14. As well, we have something called orbitals. Orbitals, okay? So the S can only hold one orbital, the P 3, and the D 5, and the F is 7. So from where these numbers comes, actually, one orbital or each orbital can only hold 2 electrons. So if the S can hold 2 electrons, this means it has one orbital. If it can hold 6 electrons, this means it has 3 orbitals, etc. So if we want to draw the orbitals, each orbital will be drawn as a box, okay? So here we have 3 orbitals for the P. For the F, we have for the D, we have 5 orbitals, and for the F, we have 7 orbitals, okay? Each orbital can hold 2 electrons. Now, based on Pauli exclusion principle, if the first electron was clockwise, the other must be counterclockwise. They cannot be the same spin. So, uphill or upward means clockwise, and the one downward means counterclockwise. You can't put 2 electrons clockwise, this is wrong. You can't put 2 electrons counterclockwise, this is wrong. They must be one clockwise and the other one is counterclockwise, okay? Hund's rule, it is another very important rule, says that when an electron is added to a subshell, it will always occupy an empty orbital if one is available. So again, when we draw the p orbital, we said that it has 3 orbitals, sorry, the p subshell, we said that it has 3 orbitals, right? Now, if we have 3 electrons in this p, how we are going to put these electrons? Now, we are going to put 1 electron in each orbital first, okay? We need to put 1 electron in each orbital before putting a second electron, in each orbital, okay? So, if we have P has 4 electrons, okay? This P, electrons will be one clockwise, the other is clockwise, and the other is clockwise. Now we have 1 clockwise electron in each orbital, then we can put 1 counterclockwise electron. Did you get it? Okay. Now, electrons always occupy orbital singly, if possible. and pair up only if no empty orbitals are available. Watch how the 2p subshells fills as we go from boron to neon. Look here, for boron, the 1s has only 2 electrons, so we have put them, and the 2s has only 2 electrons, so we have put them again. For all the atoms, they are the same. Okay, what is interesting here is the 2p, because in the 2p electrons, boron has only 1 electron, carbon 2, nitrogen 3, oxygen 4, fluorine 5, and neon 6. When it is only 1 electron, we have put it in the first orbital, 2 electrons, 1 electron in each orbital, 3 electrons, 1 electron in each orbital. When they are 4, 1 electron in each orbital, then we double the electrons in the first orbital. When they are 5, 1 electron in each orbital, clockwise, then we have double 2 of these orbitals with the 4th and the 5th electrons. And the neon has 6 electrons, 3 clockwise and 3 counterclockwise. Now we have finished the second part of chapter 1. We are going to continue with the third part, which is the last one, and the fourth one will be questions. So we are going to solve the questions about the whole chapter. Good luck. Thank you for watching.